So when we talk about the graphs of the trig functions, we do want to go back to how we define the trig functions. We know that if we're on the unit circle, by this point this should be burned into your memory. X squared plus y squared is equal to 1. In other words, cosine squared plus sine squared of my angle is equal to 1. We also know from, again, should be burned in your memory, is the sine of alpha is y over r, where alpha is in standard position, meaning that we start at the positive x-axis and rotate counterclockwise. We know that cosine, of course, is the x over r, which is just x when we're on the unit circle, just like cosine or sine is just y on the unit circle. We also know that all the rest of the trig functions become y over x, x over y, 1 over x, or 1 over y, depends on which ones that you were looking at. So these are pretty much burned into your memory by now, I hope. Yeah? Somewhat? Kind of? Okay. So if that's what we have on the unit circle, we know at this point, hopefully burned in your memory as well, if not it will be by the end of this quarter, that every time I look at the unit circle, my x values along the unit circle are related to the cosine of that angle, and the y values are the sine of that angle. Feeling it burn in your memory yet? Knowing all of this stuff, why do we learn it? Why do we care? It's because we want to be able to graph these. That's where we're going, as we are graphing these. So the first thing we're going to talk about is what a periodic function is. And each one of these trig functions are periodic functions. So we say that a function is periodic if I add some multiple to it and I get the exact same output each and every time. Basically, that's what periodic functions mean. So if I add, say, pi to my angle and I get the exact same output each time, then it would have a period of pi. If it takes me 2 pi's to get there, then it would have a period of 2 pi. So periodic functions mean that I can add some constant to my, in this case, angle, and I get the exact same answer out every single time I add a multiple of that constant. So sine, cosine, secant, and cosecant have period of 2 pi. This is kind of important, especially when we graph these. So sine, cosine, secant, cosecant all have period of 2 pi, and I'll explain why in just a moment. Tangent and cotangent have period of pi. So that's another one that you have to know off the top of your head. It'll be burned in your memory forever by the end of this. So I'm going to explain why this happens in just a moment when I give you all a chance to take a look at it. So I'll give you a moment to write that down, and then we'll go back and explain why it works out this way. Let's go back to our unit circle and explain why it has to happen this way. Now, I'm just going to pick an arbitrary angle, so I'm going to choose this one right here. I'm going to choose pi over 6. So if I look at my pi over 6, I'm going to first start with my cosine, and I have cosine of square root of 3 over 2. So I'm looking for the square root of 3 over 2. The next time I see the square root of 3 over 2 in the x position is here, but that's a negative value, so it can't be a period of rotation of 90 degrees or pi over 2. The next time I see 3 pi over 2 is here, but it's also a negative, so that cannot be a period of pi, because if I add pi over 6 and I add pi to it, I end up with a negative square root of 3 over 2, so that's not the exact same answer. So the next time I see it is right here, and it is positive. However, if I try to do this rotation of just slightly less than 2 pi each and every time, if I went back to, say, here, I'm going to choose this angle, which is 5 pi over 6. If I think it's just slightly less than 200, or slightly less than 2 pi, then going slightly less than 2 pi brings me right here. Do I have the exact same y or x value? No. So for pi, for sine and cosine, your period to get back to the exact same place each and every time to get from here back to that answer is 2 pi. So that's why sine, cosine, secant, cosecant all have period of 2 pi. It takes me one full rotation consistently to get the exact same answer back out. So then the same thing happens with tangent. So if I take this one, I'm going to take the tangent, which here is going to be the tangent of pi over 3 is a square root of 3. So I'm looking for when I have that relationship is going to be a positive. Well, in this quadrant, clearly I have a negative over a positive, so that's not going to work. But down here in this quadrant, which is a period of pi around it, I get the exact same positive answer out. So tangent and cotangent all have periods of pi because it takes me that long before I can get the exact same output out when I add a multiple of it. Does that make sense? So it is terribly important to think about what the period is when we start graphing these lovely, lovely, lovely trig functions. Okay, so that's why I have those periods. So then we know from 10.1, the arc length is defined by my angle of rotation multiplied by my r. Since we're on the unit circle, my arc length is always going to be equal to my angle. Arc length is a distance traveled. So every time I have on the unit circle, if I want to know the arc length, it is just going to be my angle, but it is a distance traveled. It is not radians, it is now a distance traveled. So if I'm talking about the arc length, and I'm saying the arc length is pi multiplied by r, where my pi and r happens to be 1, my arc length now is not pi radians. It is just pi, which is a numeric value of approximately 3.14. So that is approximately 3.14. Now this is important because we're going to unwrap this off the unit circle and put these graphs on the xy plane. So everything I put on the xy plane is an arc length, and since I'm on the unit circle, that's why I don't have to worry about the radius any longer. Does that make sense? All right. So if I look at my sine, my x being the angle I put in, so x being the angle I put in, then when I do the sine of that input, x now just being an input, it's not the x on the unit circle. X is just an input dummy variable. If I put in 0, 0 comes out. I put in pi over 6, 1/2 comes out. I put in pi over 2, 1 comes out, and etc. The ordered pairs that I'm going to write on my xy plane are here. So on my xy plane, I am going to put those on my xy plane as ordered pairs. And what I end up with is this graph right here. This is what the sine wave looks like. The key points, there are 5 key points. We always use these 5 key points. First one is 0, 0. The second one is pi over 2, comma 1. The third one is pi, comma 0. The fourth one, and these are your 5 key points, is 3 pi over 2, comma negative 1. And then my last one is 2 pi, comma 0. So those are the 5 key points. So when I say label your 5 key points with a transformation, that's what I'm asking you to do, is I'm asking you to take those 5 key points and do the transformations that are required to get from point A to point B if I have a transformation. So I'll give you a minute to write those down and to draw the sine wave. So on the xy plane, the number 1 is about right there. Here's where number 1 is, which pi over 2, which is an arc length now, so it is just a numeric value. Pi over 2 is more than 1. So if I were to overlay the xy plane with our numbering of 1 through 1,000, or -1 to -1,000, then what I would see is I'd see those numbers here lining up like this. So here would be about 2, here's about 3, here's about 4, etc. Okay? So when I am putting my pi's on the xy planes, these are just numeric values. It makes no sense for me to use the 1, 2, 3, 4, 5, 6 when everything's in multiples of pi. So they are on there, the 1, 2, 3, 4, 5 are on the xy plane. I'm just not going to use that unless I have to. because I'm going to do everything in terms of pi, it makes it so much easier because I can just take my xy plane, start at 0, and end at my period, and then cut it into the quarters that I need. So the numbers 1, 2, 3 on up are still there. I just don't use them most of the time when I'm graphing these. Does that answer your question? Okay. Anything else? Any other questions? Okay. So here's what the graph of the sine wave looks like. We talk about the fundamental cycle right here. The fundamental cycle is the cycle that goes from 0 to 2 pi. That's the blue. Now, because we call it a sine wave, it repeats itself over and over again, infinite number of times. But we usually use the fundamental cycle to do any kind of transformations and the graphs of those transformations. Okay, so the fundamental cycle is the 0 to 2 pi. We talked about those 5 key points, but if you didn't write them down the first time, here are my 5 key points. First one is 0, 0. Yes?
Why are we going, when we use 0 to pi over 2, and we have pi over 6 in between them, pi over 6 of our unit circle isn't directly in between the two of those?
Pi over 6?
Yeah, pi over 6 is closer to 0 than it is to pi over 2.
Yeah, so here's pi over 6, but I would not use that one as a key point.
Okay.
Yeah, I don't know, well, I could graph 1/2 pretty easy, right? I can graph 1/2 pretty easy, but the reason I choose these 5 key points is because I know where 1 is, and I can do the transformation on 1 easy than 1/2. So I can use pi over 6, right, here, up here. I can use pi over 6, but I don't want to.
Okay.
Just like I could use pi over 4, but I have no idea where the square root of 2 over 2 is very well. I mean, I can put it in my calculator and get an approximation, but I know where 0 is. I can draw that. I know where 1 is, and I'm talking about the outputs. I'm not talking about the inputs. I'm chasing the outputs to make my life easy in terms of graphing. So if you think about when we did the square root, if we had f of x is equal to the square root of x, we choose values that are perfect squares because we know where those are. So we can graph them, right? You wouldn't choose 3 to try to graph it, but you would choose 4 and 9 and 16 and 25. The similar thing is going on here, is I'm going to choose the ones in which I know the outputs are easily. So that's why I choose those key points. Does that answer your question?
Yes.
Okay. I'm glad you asked that question because I'm sure other people are having it too. So there are my 5 key points, 0, 0, pi over 2, comma 1, pi, comma 0, 3 pi over 2, comma negative 1, and then 2 pi 0. Those are the easiest outputs to draw. Those are the easiest outputs to do the transformations on. How are we doing? Y'all remember your transformations? I got some, maybe. Okay, same thing is going to happen with cosine. So if I do the cosine, and this is going to kind of mess you up a little bit because we're so used to having x being on the unit circle, x is the cosine value. Well, it's still kind of this way. Now remember, x is my input here. My input is an angle, but it's also, because I'm using the unit circle, is also a unit that is not in rotation. It is just, arc length is just a length. So my cosine wave, if I use, again, I can use any of those numbers, right? I can use pi over 3, I can use 2 pi over 3, but then if I use those, then I have to find out where 1/2 is, and I don't want to chase 1/2. I want to chase only the outputs I know the best, and so without doing any work, I know that this is my first key point, this is my second key point, here is my third key point, my fourth key point, and my fifth key point, because I can easily find 1 as an output. So if I move this over so you can all see the sine wave, or the cosine wave, here's what the cosine wave looks like. My key point, my key point, my key point, my key point, and my key point. Because I can easily find an output of 1 versus 1/2, or versus the square root of 3 over 2, or the square root of 2 over 2. I could put those other ones on there, but I don't want to. Yes?
Are your inputs always going to be the x value?
Inputs are always your x value, yes. So what we're going to see this as is we're going to see f of x is equal to the cosine of x, and x being the input, which is the arc length, which is just the angle but no radians anymore. So, since we're talking about that anyways, let's discuss the quadrants. What is my first quadrant? On your unit circle, where's my first quadrant? Where does it start and where does it end on my first quadrant? 0 to pi over 2. That's quadrant 1. Where's my next quadrant? Pi over 2 to what? Pi. So there's quadrant 2. What is my next quadrant? Pi to 3 pi over 2. Here's quadrant number 3. And then my last quadrant, of course, is okay. Any questions so far? And this is going to be true no matter what trig function we're using, quadrant 1, quadrant 2, quadrant 3, quadrant 4. So if I look at my cosine wave, right, if this is quadrant 1, then this one must be quadrant 4. If this one's quadrant 2, this one must be quadrant 3. If this one's quadrant 3, then this one must be quadrant 2. If this was quadrant 4, then this must be quadrant 1. This direction, we are going our regular counterclockwise. That's why those are all positive answers. So this is our regular counterclockwise. On the unit circle. In this direction, I'm going counterclockwise. Or in other words, I'm going clockwise, which is on the unit circle. So that's why we're going in negatives. It's a negative pi over 2 because I'm going in the negative direction. So we're going clockwise on the unit circle. And that's how come you see negative pi over 2. That's in quadrant 4, going backwards. So you're going, for us, going backwards is clockwise in trig. Any questions on that? Because this whole concept of going backwards is going to be extremely important. So if there's questions on these quadrants, now is the time to ask. Yes? The cosine wave? Do you want me to erase the stuff I wrote all over it? Are you sure? Because I don't have a problem erasing all that stuff. Okay. I have some skills. Not very often, but I have some skills. And that way you get just to see the bouncing ball too. That's kind of cool, right? So the question is, where are these outputs coming from? Can I go back to the unit circle? Okay. So let's go back to our unit circle up here. Or not. So as I go back to my unit circle, and as I'm looking at my unit circle here, I am going to just focus on the x values for the cosine, right? So if I'm on the unit circle and I am asking you for the cosine of 0, the cosine of 0 is 1. And if I'm asking you for the cosine of pi over 6, it's a square root of 3 over 2. If I'm asking you for the cosine of pi over 4, it's a square root of 2 over 2. If I'm asking you for the cosine of pi over 3, it is 1/2. If I'm asking you for the cosine of 90 degrees, it is 0. So if I'm asking for the cosine of pi, it's -1. If I'm asking you for the cosine of 3 pi over 2, it is 0. Those are my key points.
I think the one that we just did, though, there was a 2 as a alpha.
2 pi?
No. Here's one I thought that was.
That's okay. Are we okay? All right, so then, again, I'm gonna flog these like a dead horse. These key points are terribly important. So if you don't have those key points wrote down, make sure you write those down. The key points are 0, 1, pi over 2 comma 0, pi negative 1, 3 pi over 2 comma 0, and then 2 pi comma 1. And if you ever get stuck on deciding which wave starts at up and which wave starts at 0, 0, is just look at your unit circle. Your unit circle is going to tell you which wave starts here at 1 and which wave starts here at 0, 0. And that is at the 0 for the angle of 0. Questions? Okay, cool. We talk about amplitude. When we talk about amplitude, it is the distance from the x-axis to a maxima or a minima. So when we talk about amplitude, it is the distance from the x-axis, if there's no transformation, to a maxima or a minima, the extremes. Now I say from the x-axis, but if we have a movement up, then we say it's from the baseline. So the amplitude is the distance from the baseline, or in other words, the x-axis, if there's no translation up or down, to a maxima or a minima. Which functions do you think will have an amplitude, and which functions do you think will not? Sine has amplitude. Who else has an amplitude? Cosine. Do you think any of the other ones will? No. The only ones that have amplitude are sine and cosine. So when we talk about an amplitude and I give you a tangent, I ask you for the amplitude of a tangent, you're going to say none. Because we're looking for a maxima or a minima. So the only ones that have it are the sine and cosine. So as a recap, which functions have periods of 2 pi? Sine and cosine. Who has periods? Oh, not just sine and cosine. Who else has periods of 2 pi? Cosecant and secant. The reciprocals also have period of 2 pi. Who has period of pi? Tangent and cotangent. Okay, so let's talk about we'll start with the cosine. The domain of the cosine is everything. And this is going to be so important. You're going to put anything you want in cosine. Put anything you want in cosine. Any real number will work. Because remember, now we are on the xy plane, so pi is just 3.14 each. So if you put 1 in there, make sure your calculator is in radians. Your domain is -1 to 1. Or your range is -1 to 1. Notice the lowest output you're going to get on the unit circle for cosine is -1, and the highest is +1. It is a smooth and continuous curve. That's going to be important when you guys get into Calc 1, when you start doing derivatives. It is even. What that means is I have symmetry with respect to the y-axis. That means if I can draw one side of the graph on the right side of the y-axis, then it has a mirror image across the other side. So this is where the odd and even is nice. Has period of 2 pi. I'll give you a moment to write that all down. So for sine, we have the domain is everything again, so -infinity to infinity. It has a range of -1 to 1. It is smooth and continuous, and this is going to be important when you get into calculus. There's a smooth and continuous curve. That means when you get into calculus, you get to do the derivative everywhere on its range, on its domain. It is an odd function, which means we have symmetry with respect to the origin. It has period of 2 pi as well. So our graphs will be of this form. Y equals A, sine omega, x minus phi plus b. Now, if you're thinking this looks foreign, what I'm hoping does not look foreign is this. G of x is equal to a f of b x minus c plus d. Now, that's something you all should be familiar with from your last math course. It is the transformations of graphs. So if you were in my class, I flogged that thing like no other. We spent a lot of time on doing the transformations of graphs. If you weren't in my class, now is an opportunity to get really good at transformations of graphs. Giving you opportunities here. So we're just going to call these slightly different things, but it's still B, it is still C, still A, still D. We're just going to call them slightly different things. The A is your amplitude. So if that is 3, we would have said back in pre-calc 1 that we would have had a vertical stretch by a factor of 3. In trig, we say the amplitude is 3, if it has an amplitude. If it doesn't have an amplitude, then we say it is vertically stretched by a factor of 3. Omega, or that W, is our period change. If our omega is 1, our period is the same as we normally have. But if that omega is 2, then our period is half as big as we used to have. So if it's inside the function, it does the exact opposite of what we want it to do. Your phi is your phase shift. That is, you're picking up, moving it left or right. And it always goes in the opposite direction of what we want because it's inside of our function. I'll give you a moment to write all that down. B is your vertical translation, just like it was before. It's outside of the function. It's affecting your range. So it is moving it up or it's moving it down. And the way that we define our period is, because it is the opposite of what we expect when it's inside of the function, our period is always going to be whatever the period is for that function to begin with. So if it is 2 pi, I do 2 pi. And then I divide by that omega. So as an example, if I have the sine of 5 x minus pi over 2 plus 3, we'll put a negative 2 right there, then what does the negative do to my graph when it's outside of my function? What does that do to my graph? Flips it how? So it is going to do a reflection across the x-axis. So the negative is going to do a reflection across the x-axis. So what that means for my graph is instead of going at 0, 0 and going up, I'm going to go 0, 0 and go down. So that's what that part is going to do. Okay? The negative, just the negative part. What does the 2 do to my graph? It's a vertical stretch. So instead of having my graph go from 1 to negative 1, it's going to go from 2 to positive 2 to negative 2. So far what we have is this graph is going to look like this. Not drawn well, but it's going to go up to 2 and negative 2. Go down to negative 2. What does this 5 do to my graph? It is a horizontal shrink because it's inside my function. It does the exact opposite of what I'd like it to do. So what happens here is I take my 2 pi, because the period of sine is 2 pi, and I divide it by 5. This is my new period. What that means is my graph, instead of starting at 0 and ending at 2 pi, it's going to start at 0 and end at 2 pi over 5. So far, this is what my graph looks like. I start at 0, 0. I'm going to go down to 2, up to 2. And instead of ending at 2 pi, I'm ending at 2 pi divided by 5. So 2 and negative 2. What does that pi minus pi halves do to my graph? So I'm going to go right pi over 2. This thing is going to move everything right. It's a phase shift. We're picking this up and moving it. It's a phase shift. So it's going to go right pi over 2. So what my graph now looks like is it's going to start, instead of 0, 0, it's going to start at pi over 2. And it's going to end at 2 pi over 5 plus my phase shift pi over 2. It's going to start down, go up, and look something like that. Not drawn well, by the way. Let me try that again. So it's going to look like this. So that's where we are so far. So 2 and negative 2. Yes?
When you're at the points on the x-axis, can you just keep it like the plus? Or do you have to actually...
You actually have to find it. Yeah. Which if you want, we can do it right now if you want. Let's do it right now. Yeah. So let's just go ahead and figure out where that ends. So I'm adding 2 pi over 5 plus pi over 2. What is my common denominator? 10. So I'm going to multiply here by 2, here by 5. So I'm going to have 4 pi over 10 plus 5 pi over 10. So what is that value then? 9 pi over 10. So let's just go ahead and write 9 pi over 10 there. I was being lazy. Thank you for catching my laziness. 9 pi over 10. How are we doing? All right. The last piece is the up 3. What is that? I just told you. I'm going to go up 3. Okay, so let's bring this all together as my final graph. Now, this point right here is, I should have gone down to negative 2. So I know that this is at negative 2 and this is at positive 2. I know I'm going to start at pi over 2. I know I'm going to end at 9 pi over 10. I'll have a halfway mark in which I'm crossing the x-axis before the shift up. I would have had the quarter mark, and we'll find all these in a minute, the quarter mark in which I would have had my absolute minimum, and then I would have found the other quarter mark in which I would have had my absolute maxima. So I also need to move up 3. So I know that this is my starting point, this is my ending point on my shift up. We're going to find our halfway mark and we're going to find our quarter marks. So it's now just a matter of making sure that we have our y's correct. So I go down initially to negative 2. I'm adding 3 to it. So where do I go down to now? So I'm going to go down to 1. So that's going to go there. So I'm going to start here. I'm going to go there next. And then I'm going to go right there because that would have been on the x-axis. That would have been my 0, 0. Yes?
Shouldn't it be 5 on top? Because you went from 2 to 3.
It's because the negative to begin with in the very beginning, I have a reflection across the x-axis. So instead of going into a maximum like I normally should do for a sine wave, because I have a negative 2 in front, I'm going to go into a minima first. So here, right back here, that reflection is why we end up going down first instead of up first.
No, well, like the value of positive and negative shouldn't be 5 because you're adding 3 to everything, so it should get up 3.
So negative 2 plus 3,
Yeah.
which 1. So that's that one.
Shouldn't the top have 2?
Oh, yeah, I'm not there yet.
The 3 is just for the baseline.
No, you were giving me an answer I'm not ready for yet. We're getting there. So, Ryan, what is my next point? You just told me. You got me lost too. It goes up to 5. So that was you were giving me 5. I just wasn't at that point yet. It's at 5. And that's the 2 plus 3. And then I go back to here. And so this is my sine wave. That's my sine wave. Yes?
Do you always have to incorporate your vertical
No, so you can do your translations in any order you want, but the best order, if we go back to here, the best order is to do this one first. We want to do first, the easiest thing to do is to always do your period change first. That's the thing you want to do first. So it is the easiest, but you don't have to do it that way. So if you're graphing these, the first thing you want to do is your period change, because then you compress it or stretch it, and then what you're going to do is you're going to move it left or right. Once you move it left or right, then you're going to determine what happens to your amplitude, and lastly, you actually move it up. The order doesn't matter, but this is the easiest order not to get messed up.
Right, but if you were to add 3 to the 1, so let's say you did your vertical transformation first, you would get 4, and then you would multiply that by 2, so then you would get 8.
Because this is why it's important to try to keep it in this order, otherwise what you're doing is incorrect.
Okay.
So you notice how I did it here, I did it step by step. What I did not do is I did not take my maxima way back here and coming in with my regular sine wave. Here's my regular sine wave. What I did not do, going from 1 to -1, what I don't do is take and add 3 to that first and then do the stretch. You don't do it that way. I mean, the order doesn't matter, but what you do to it does matter. So notice I did this strictly left to right. I started with the amplitude change, then I went into the period change, then I went into the phase shift, and then I did the vertical. But it is in your best interest to do it in this order almost all the time. Because otherwise what's going to happen is you're going to get those max and minimums values that are incorrect. Just like the moving left and right, I would suggest you don't do that until you've done your period change. So you can, the order doesn't matter as long as you're doing what is needed correctly. Does that answer your question? Okay. So any other questions on this here? Yes?
So do we still need to find the values in between?
Yeah, let's find the values in between.
Are we always going to have to do that? Or?
Yeah, you're always going to have to do those values in between because I'll ask for the 5 key points. Now the y values are the easiest parts, right? The y values are cool, they're easy. It's these other ones is going to mess you up if you're not cool with fractions. That's where we're going to have issues. So what we know is that this point right here is halfway between the pi over 2 and the 9 pi over 10. It is the halfway mark. Now either A, you transform each x value individually, or B, you get your starting point, your ending point, divide by 2, and that'll get your halfway mark. Divide by 2 again, that gets you the quarter mark, and then add that to the half mark. That is the easiest way to do it. But if you want to do a transformation on each key point, you can do that as well. I will do it both ways. So if I want to find that part, then what I'm going to do is that is going to be equal to my beginning plus my ending divided by 2. That's where that key point has to be. It is halfway between the beginning and ending. So I just do the addition of these fractions. So for the addition of these fractions, then what I'm going to do is my favorite thing, multiply by the lowest common denominator everywhere, which is 10. That will give me, when I multiply 10 by pi over 2, I'm going to get 5 pi. When I multiply 10 by 9 pi, I'm going to get plus 9 pi. And then the denominator, I'm going to get 20. So I end up with 14 pi over 20, which reduces to 7 pi over 10. So the halfway mark is 7 pi over 10. Now, to find this key point, what I do is the same thing. Is I'm going to take pi over 2 plus 7 pi over 10. I'm going to divide it by 2. So again, I'm going to multiply by 10, because that is my lowest common denominator. So I will get 5 pi plus 7 pi all over 20, which gives me 12 pi over 20, which is equal to, reduced by 4, So 3 pi over 5. So this is 3 pi over 5. I'm going to do the same thing for this point. I'm going to take my beginning, which now is 7 pi over 10, plus 9 pi over 10, divide it by 2, multiply everything by 10 again, and I end up with 7 pi plus 9 pi all over 20, which is 16 pi over 20, which reduces to 4 pi over 5. So this one is 4 pi over 5. Now, tomorrow's lecture, we're going to do it again, but we're just going to hit the key points and we're going to do it by transformations.